Hello everyone. In this lesson, we're going to basically do the same thing we did in the previous lesson, go through a curve sketching procedure, but we're going to do it with a rational function. Okay. So as a quick review here, what are some of the key things that you need to graph a rational function? So the main thing we're going to have to watch for here, right, is asymptotes. Okay, because there's three different kinds that could show up in a rational function. Okay, there's the vertical type. Okay, and those come from the roots of your denominator. Okay, there's a horizontal type. Okay, that occurs if the degree of the numerator is less than or equal to the denominator's degree. So for example, if you have like x squared over something with an x squared, it's going to have a horizontal asymptote. If the degree is greater on the bottom, like if you had like, x plus 2 over x squared minus 4, okay, that would be a horizontal asymptote of 0. Okay. Okay. If the numerator has a bigger degree, specifically if it's 1 more, then you get an oblique asymptote. Okay, and it follows some kind of a line. Okay, and we won't get into that right here, but by extension, right, if this was like 2 more than the numerator, you would have a parabolic asymptote. Like the degree of separation kind of determines what the function approaches at the extremes. Okay, so those are the three types. Okay, so right, from advanced functions, be familiar with how to set those up. Okay, one thing I am going to mention as I get into this example, okay, or two things. One, this is not the same example that's in the online notes. Okay, so the online notes is a slightly different one, which covers a different type of asymptote. Okay. Second, okay, I pre-wrote this one out because I know in the previous video I kept making little errors, and I just don't want the video to go on and on and on. There's nothing wrong with showing errors. I think it's good to show that, I make them too when I'm running through problems. But yeah, so this is pre-written up, and I'm just going to highlight things as I go. So we're going to try to sketch this function, x cubed over x squared minus 12. Okay, so our first thing we're looking for is our domain. Okay, we know that the potential issue occurs at asymptotes. So I need to figure out my roots. So as a quick side check, right, I find the roots in my denominator, okay, and they turn out to be plus or minus 2 root 3. Okay, so my domain is everything except those locations, right? So from negative infinity to negative 2 root 3, between negative 2 root 3 and positive 2 root 3, and from 2 root 3 over to infinity. Okay, again, for reference, 2 root 3 as a decimal is about 3.5. Okay, it's 3.46. Okay, so when we're actually graphing it, that's how we'll put it on the graph, is noting it's about 3.5. Okay, our second thing is intercepts. Okay, so for the x-intercept, right, I just set my function equals 0. Okay, and I note my restrictions. Okay, when I multiply the denominator up, it also becomes 0. So I just have x cubed is equal to 0. So that means x is equal to 0. Okay, for my y-intercept, that occurs when x equals 0. But as I just established, that's at 0. So it's going to be 0 as well. Okay, next thing is asymptotes. Okay, well, we already noted our vertical asymptotes. Okay, they occur at plus or minus 2 root 3. Okay, comparing the degrees, okay, the numerator has a degree 1 larger than the denominator. So that means that this has an oblique asymptote. Okay, the way you find an oblique asymptote is by forcing long division on the function. So I'm going to divide x squared minus 12 into x cubed. Okay, and I've written out the placeholders. I had no x squareds, no x's, and no constants. I guess that should be a plus, but it's okay. So when I multiply it by x, I get x cubed minus 12x. Okay, when I subtract, should just be positive 12x there. But I can't do anything more because this degree is higher. So that's my oblique asymptote. Okay, so my oblique is the line y equals x. So this function has three asymptotes, two vertical and one oblique. Okay, our next thing to check for is symmetry. Okay, so we're going to substitute in negative x and see what happens in our function. So in the numerator, I'm going to get negative x cubed. I have three negatives, so it'll stay negative. In the denominator, the x squared removes the negative. Okay, but I can pull that negative out in front of the function, right? This negative can just sit out front. So that means that I have odd symmetry, right? This is the negative of the original function. So this will have odd symmetry when we get to that point. Okay, so we've done all our work with the regular function. Now it's time to look at the derivative. So for reference, here's the original function. Okay, it's rational, so it's a quotient. So we're going to use the quotient rule to figure this out. Okay, so, right, derivative of the top, which is 3x squared, times the bottom, x squared minus 12. Subtract the top, x cubed, minus the derivative of the bottom, which is 2x, and that's all over the denominator squared. Okay, now it's just a matter of tidying this up. Okay, so we expand out our numerator, okay, and tidy that up a bit. Okay, and I know I'm going to need to look at the critical numbers in a minute, so I'm going to keep factoring this. So I common factored out x squared. And now this is the difference of squares. Okay, so there's all my different things. Now, a new thing to note here, and this is a different, in the note we said our critical points, critical points occur where the derivative is equal to 0. But in terms of our critical numbers, okay, I do have to consider the asymptotes, okay? Because an asymptote is where the function could potentially switch from increasing to decreasing, okay? If I have my vertical asymptote, and let's say my function approaches it like this, okay, then on the one side it is increasing, the other side it is decreasing, so it could switch. So we have to expand our definition of critical numbers. They also occur where the function is undefined, okay? There could be something happening there. I need to check it out, okay? So that part is new. Now, in terms of my denominator, I pretty much have the same thing I had before, it's just squared. So my asymptotes are going to be those new critical numbers. This means we got to make a pretty big chart because I've got 5 critical numbers there. So there's all my intervals. Okay, here's all my factors. Okay, and again, I filled this all in. Some notes for speed's sake here, right? My two things that are squared, right, this and this, they have to be always positive. So those rows were really easy to fill in. Okay, and then for the other intervals, we just did test values to go across. So this one is almost always negative. This one is almost always positive. Okay, so overall, my derivative is positive, and then it's negative for quite a while, and then it is positive again, which means my function is increasing at the start, decreases a long while, and increases again. Okay, now it's decreasing on both sides of my asymptotes. Okay. So this is a local max here. This is a local min here. Let's mark these off. This was the vertical asymptote. Okay, and this was also a vertical asymptote. So those are not maxes or mins. Okay. This part in the middle, okay, this is a point. This is the x-intercept at 0, which is also the y-intercept. Okay, this is a case where, right, it's decreasing and then decreasing. So it does not have a local max or min there because it didn't switch. Okay. Okay, so now we know where local max and mins are. Okay, again, I'm not going to show the step, but the way we got -6 and -9 is I went back to my original function and I plugged in -6 and worked it all through, and you end up getting -9. And similarly over here. Okay, now that we've done that, we go on to the second derivative. So here's my first derivative. Okay, and now I have to take the derivative of this. Okay, and if you're already saying yuck, okay, I don't blame you. It's just a bunch of algebra that we have to push through. So the derivative of the top is 4x cubed minus 72x times the bottom. Okay, the top, right, so subtract the numerator minus the derivative of the denominator. Okay, this has the exponent, so we have to go to the chain rule. Okay, I bring down the 2. Okay, leave the inside alone, and then I do the derivative of the inside, which is 2x. Okay, over the denominator squared, so it's going to be power 4, right? I've got x minus 12 squared, so it's 4. Okay, all of my terms in the numerator have an x squared minus 12, or I shouldn't say terms, my little sections here that are all multiplied together. So I can common factor out an x squared minus 12. Okay, in terms of tidy up, that means I can remove this and I can reduce this exponent to 3. And now I just have to work on expanding and simplifying this lovely part right here. Oops. So I'll save the details. When we run that all through, we get 24x cubed plus 864x in the numerator. Okay, I know that I'm going to need to do some factoring here, so we're going to do that next. Okay, and we're good. So potential inflection locations. Okay, same as before, right? I have a root. This gives me 0. So there could be an issue at 0 or an inflection point there. Okay, I have to include my asymptotes because when I flip from side to side, it could switch concavity. This factor has no roots, right? If I tried to solve it on the side, it would be x squared equals minus 36, okay, and that has imaginary roots. So we're not going to worry about that part. So once again, we make a chart. There are my intervals. Okay, and in terms of my pieces, okay, those are the different pieces that I have. So I have 24, the constant. I have a solitary x. I have x squared plus 36, and I have x squared minus 12, all cubed. Okay, so the 24 is always positive. For x, it's negative below 0 and positive above. This term, okay, it has no roots, right? This part is always positive, and then plus 36 more, so it's going to be positive. Okay, and then for the last piece, it did some testing, okay, and it's positive on the outside and negative in between. So what does that tell me? Okay, for my derivative is negative, then positive, then negative, then positive. So in my original function, it is initially concave down, then it is concave up, then concave down, then concave up. So at my 2 asymptotes, right, again, I'll just mark those here. This was an asymptote, and this was an asymptote. It switches concavity on either side of the asymptote. Okay, and it also has an inflection point, okay, which we kind of predicted, I think, in the last chart at 0 and 0. Okay. So now that I have all that information, okay, there's a lot of stuff there, we can put it together into a graph. So I've pre-drawn the asymptotes, which are at about 3.5, positive and negative, and my vertical, my oblique asymptote, which I should move up a tiny bit there. Okay, I had a root at 0 and 0, is right here. Now, I know this came up a bit in the last assignment. A few people asked me about this, because this might look weird that there's a point on the oblique asymptote. Okay, that is okay. For horizontal and oblique asymptotes, they are really guidelines for end behavior. You can break through them in the middle of the function, and that is totally fine. Okay, it is. All right. Vertical asymptotes, no, because if you broke through a vertical asymptote, you'd really kind of it wouldn't be a function anymore, because you have 2 different things happening at the same value of x. Okay, but horizontal oblique, yep, go for it. Okay. So we had a local max and a local min. Okay, so we have a max at the point 6 and 9. So up here, okay, and a point at -6 and -9. So down here. Okay, I have an inflection point in the middle, right there. Okay, so what does this function look like? Okay, some other information I really should use here is the increase decrease part. Okay, we said it was increasing up until that first max and min. It's decreasing everywhere else. Okay, we also said it was concave up. It keeps flipping back and forth. So like this is all concave down. This part is concave up. Okay, and it has to be decreasing. So it starts here and must head towards this point in the middle. Okay, this is concave down. Okay, and it's still decreasing, so it must go this way, right? It's decreasing on this interval. So the function is going to look something like this. Okay, it was increasing, okay, until we get to that max, and then it starts decreasing towards the asymptote. Okay, in the middle, it was decreasing. So that means I have to start up here, come down. Okay, I have an inflection point, so it twists. Okay, it twists, and I know that the derivative that had a tangent of 0, so it has to get kind of flat there for a second, and then keep going down. Okay, and then it still decreases from here. Oops. Okay, from this asymptote it decreases, hits the local minimum, and goes back. Okay, so a funny looking function, but that's how it works. Okay. So yeah, because I knew the function was negative, right, or decreasing all the way through, it had to start up high to be able to decrease through here and continue decreasing through there. Okay. So for practice, starting on page 183, here's some questions you can look at. Okay, and again, do as much as you need to. Like some of these first ones just asking you to find asymptotes, that thing. So just review as much as you need to for advanced functions and then keep going. But make sure you do a couple of graphs. Okay. Thanks for watching. And as always, if you have questions, please send them along.